Let me get this into present. Here we go. This is my Module 3 Mastery assignment. So some important terms for the first part are, here they are. Convergence is a series, means that a series has a sum. Divergence means that a series does not have a sum. And just to clarify, I probably should put that one first on the list. A series is a set of terms being added together. So sigma notation is a way of writing a series using the Greek letter sigma. And some special types of series are here are three types. The first one is a p-series, a series which converges or diverges depending on the value of p, and I'll clarify that in a couple minutes. A telescoping series, in which the terms eventually begin to cancel each other out as n approaches infinity, and a geometric series where each term can be multiplied by a common ratio to determine the following term. So the convergence of a special series, a geometric series. So if you have the sum of r to the nth power for n equals 1 and continues to infinity, and just to clarify, this works for n equals 0 also, but in all the examples I'll be using n equals 1. And so it works just the same. If r is less than 1, the series converges. If r equals 1, the series diverges. And if r is greater than 1, the series diverges. So here's how you determine the convergence of a p-series. If it is the sum from n equals 1 to infinity of n to the negative p, or n over p. If p is less than 1, then the series converges. And I don't know why I wrote that. I apologize. That should say diverges. If p is less than 1, the series diverges. If p equals 1, the series diverges. And if p is, but in that case, it's called a harmonic series, so it would be 1 over 1 minus plus 1 over 2, plus 1 over 3, plus 1 over 4, all the way to 1 over n. And of course, n is approaching infinity. So even though the terms approach 0, it still does not converge. So if p is greater than 1, the series converges. So the last series that we're going to be talking about is a telescoping series, in which I think I had the right setup for that. It would be c divided by n times n plus c. And what you can do is for n equals 1 and continues to infinity, I believe that most of the series should work if n equals 0 too. But in this case, like I said, I'll be using n equals 1. So basically, you can use partial fraction decomposition to break that down, which should give you 1 over n minus c over n plus c. Because when you multiply it across, you have to cross multiply both denominators. So what you'll get is you'll get n plus c minus my bad. You'll get n plus c minus n, because when you multiply negative 1 times n, you get negative n. So when you when you break apart the denominators, you'll get 1 over n minus 1 over n plus c, because when you multiply them across, it cancels out to c over n squared plus nc. So it's called a telescoping series, like I said, because think about how a telescope collapses, and that's because the terms will eventually cancel each other out, because in each term it can be broken into not too smaller terms technically, but it would, like, take for example 1/2 minus 1/3. One is going to be positive and one is going to be negative, and eventually one of the terms that are negative in one will be a positive term in another, so they'll begin to cancel each other out. So it goes something like a minus b plus b minus c plus c minus d, all the way to 1 over n minus 1 over n plus c. So you see in this case, the b's cancel each other out, the c's cancel each other out, and d would eventually be canceled out. So the sum of it is just a. So here's some examples. So just because telescoping series, if it's telescoping, it will always converge. I decided not to include examples, but I did include p-series and geometric series. So let's just say you have the sum for 1/2 to the n for n equals 1 and continues to infinity. That is convergent because r is less than 1, because r is 1/2, because it's r to the n, and which is 1/2 to the n, and 1/2 is less than 1. Therefore, it's convergent. So then the second one is the sum of, and I apologize for the ones looking like a problem number. That's just the way the spacing worked out. So for the second one, it is the sum of 2 to the nth power for n equals 1 all the way to infinity, and it's divergent because if it's r to the n, and that means 2 is r and 2 is greater than 1, making it divergent. So those were geometric series. Now for p-series, we have the sum of n to the negative second power, or 1 over n squared, for n equals 1 to infinity, and that is convergent because if it's n to the negative p, then that means that negative p equals negative 2 and p is 2, and since p is greater than 1, it converges. So for our fourth example, which is also a p-series, we have the sum from n equals 1 to infinity of n to the negative first power, which is 1 over n, and since it's 1 over n, that would be n would be to the negative first power, p would be 1, and even though the terms approach 0, as do the terms of most other p-series, it still does not converge because p is less than 1, so that means it's divergent. And that would actually be a harmonic series right there, because it's 1, because p equals 1. So our next topic will be the sum of a geometric series. So most of the terms are the same again. The only one that I believe I added on was a common ratio, which is common ratio is an integer r such that r is less than 1 that can be used to find the following terms in the series. Now I apologize because r can be greater than 1, but when we're talking about convergent series, r has to be less than 1. But yes, there can be a divergent series in which the common ratio is greater than 1 or equals 1. So I apologize for that mistake. So the sum of a geometric series can be found using the formula of 1 divided by 1 minus r, and that's not the actual sum, but that's part of it, where r is the common ratio in a series. So if you have the sum of r to the nth power for n equals 1 and continues to infinity, and r is less than 1, then you can find it by multiplying the first term, which in this case would always be r for n equals 1, and if n equals 0, then the first term would be 1. And what you do is you multiply r times what you get from 1 over 1 minus r. So technically the sum of a geometric series is the first term divided by 1 minus r. So an example of the sum of a geometric series so our first example is the sum of 3/4 to the nth power for n equals 1 and continues to infinity. So the sum of that is r, which in this case is the same thing as the first term, times 1 over 1 minus r. So r in this case is 3/4. So it is 1 minus 3/4. So 1 minus 3/4 is 1/4, and 1 divided by that is 4, and then it is 3/4 times 4. So that gives us 3. So for our second example, we have 1/3 to the nth power for n equals 1 and continues to infinity. So in this case, since r is 1, it's 1 divided by 2/3, which is 3/2, times 1/3. The 3's cancel out, and you get your sum to be 1/2. And I apologize because the free recording limit is about to run up, so I did rush right there at the end.